Look at these two web layouts. On the left, a standard 50-50 column split creates a layout that feels cluttered and difficult to navigate. On the right, the columns are asymmetrical, and the composition feels balanced and intuitive. That sense of balance on the right is the direct product of a specific, reproducible mathematical framework. This is the growth pattern of a nautilus shell. Its chambers expand outward in a continuous sequence. This progression is driven by the Fibonacci sequence, an additive series where each number is the sum of the two preceding it, which serves as a blueprint for structural balance in the natural world. We can translate this biological code directly to a digital canvas. We are going to take a flat 1200 pixel wide mockup and apply 3 specific mathematical steps to establish its structural layout. Calculating these spatial proportions removes the guesswork from the layout process, resulting in a design that aligns with the organic patterns of growth found in nature. Step 1 is defining the main grid. A common industry practice is to divide a web page into 2 equal halves. However, an even split creates visual competition, as the eye has no clear starting point. To solve this, we use the relationship between the numbers in the Fibonacci sequence. As the sequence progresses, the ratio between any number and the one preceding it converges on 1.618, the golden ratio. This will be our precise layout multiplier. Here is a standard 1200 pixel wide container. To determine our primary column width, we divide that total width of 1200 by 1.618. This yields approximately 742. This calculation provides a 742 pixel primary content area and leaves exactly 458 pixels for a secondary sidebar. If your calculation ends in a decimal, simply round to the nearest whole pixel. The visual impact of the ratio remains intact, even with minor rounding. These mathematically derived asymmetrical columns create a natural visual hierarchy. The larger space commands attention, guiding the user to the main content area first. Step 2 applies this math to vertical text sizing. Relying on arbitrary font sizes can break the visual harmony established by the grid. We start with a baseline body text size of 16 pixels to serve as our mathematical foundation. To find the size for the next level heading, our H3, we multiply that 16-pixel base by 1.618. This gives us 26 pixels. We apply the same multiplier to our new heading. Multiplying 26 by 1.618 gives us 42 pixels for our primary H1 heading. This mathematical scale ensures that every text element relates to the others. The headings and body text feel unified, helping the user distinguish between different levels of information. Step 3 is the placement of key interface elements. While the rule of thirds uses a static grid, the Fibonacci spiral provides a dynamic path for the eye to follow. The origin point of the spiral, its tightest coil, serves as the natural anchor for the page's most critical element. To use this tool, overlay the transparent spiral onto our 742-pixel content area, scaling the outer curve to the container boundaries. Position your primary call to action inside the center of that origin point. Finally, align supporting elements along the spiral's sweeping arc. The spiral creates a continuous visual momentum. It guides the user's eye from the broad information at the top of the curve directly toward the primary action button. Look at the final comparison. We have moved from a series of unstructured boxes to a layout where every element has a defined, proportional relationship to the others. The resulting visual journey is clear. The user enters at the heading, follows the curve through the content, and arrives at the intended destination. This improvement was achieved by applying the Fibonacci sequence to our columns, text, and placement, replacing subjective preference with a structural system. Open an active landing page design and apply these 3 steps. Calculate your columns using 1.618, scale fonts by that same ratio, and check button placement with the spiral. Adopting these mathematical principles shifts UI design away from guesswork and towards a system of objective structural competence.